Okay, so the two exercises we practice right now are related to the integration problems. So sometimes we need to answer how long and how large the time required to satisfy certain conditions. Okay, so but the following slide we move to different topic. Right now we wondering to apply the continuity equation, but the condition we change to the pipe flow. So as I mentioned before, in the pipe flow, if you depict the control surface, okay, and you will define the control volume inside here. But as you can see in the pipe flow, we can say that the mass in the control volumes didn't change with the time, because in the pipe flow, the water in the control volumes always stay there, cannot dissipate and cannot disappear, and also the space is limited, so it cannot accumulate additional water inside. Okay, so when we discuss with the pipe flow, we always say that the dmCV dt is always equal to the 0. Okay, so in the continuity equation, we only have the items related to the control surface. We only have the items related to a control surface. So that indicates all the outflow integrate minus all the inflow integrate all the mass rate will equal 0. Okay, so in the following, we have the exercise and we focus on the topic is the pipe flow. So if we see the problems associated with the pipe flow, so we don't have the dmCV dt items. That indicates the mass in the control volume did not change with the time. Okay, and so this is the formula, the continuity formula for the pipe flow. But one important thing I would like to emphasize, because right now the condition we consider is the steady flow. But if your flow is unsteady, it is possible to have some accumulations in the control volumes. Okay, if your flow is unsteady flow, you may involve some mass changes in the control volumes. Okay, so the continuity equation showing here only satisfy when we discuss the flow is steady flow. Okay, so it's a very simple exercise. We have we depict the control surface, and inside there is our control volumes. So we can draw the two cross section line, the cross section 1 and the cross section 2. So the cross section 1 here is our inflow, and there is our outflow. And as you can see, the diameter of the different cross section area is different. And so the first, we know that the continuity for the pipe flow is the rho 1 and the A1 cross section area multiply the V1. Here I don't use the integration because the flow is uniform flow. So the uniform flow indicates all the cross section area with the same velocity. So that's why I just directly write down the continuity equation is rho 1 A1 V1 is equal to the rho 2 A2 and V2. And sometimes we assume the flow is incompressible, right? That's why the reason, because our fluid topic is the water, not the gas. So the water always we can say that the incompressible flow. So that's the reason we can say that the low 1 will equal to the low 2. Okay, the density is the constant. So we can rewrite the equation is equal to the A1 V1 and equal to the A2 V2. Okay, and then we have known the velocity V1, but we didn't know the V2. So I keep the unknown parameter on the left hand side, and the right hand side I have the A1, A2 ratios and multiply the V1. And since we know that this is the pipe, so the A1 cross-section area equal to the 4 over pi over 4, right? And the D1 square. This is A1. And the divided, the A2 is pi over 4, but the D2 square. Okay, and then multiply the V1. So we know that the ratio of the area can be changed into the diameter D1, D2 square and the V1. So, and the D1 is here is the 1.2 meters, and the D2 is 0.6 meters, and the square and the multiply the V1 is 2 meter per second. Okay, so this is will equal to the 8 meter per second velocity. Okay, so this is a very simple idea, but if you compare to C, because the D1 to be a D2 to become a small cross-section, right? Become a small cross-section area. But as we can see, the V1 initially is 2 meter per second, but we'll change it to into the V2 is 8 meter per second. So small cross-section area will have a large velocity, right? So let's keep the idea in mind is the small cross-section area velocity will increase. So that means if a large cross-section area, the velocity will decrease. It's just a very common sense and very easy to identify and remember. So another question is we discussed with the problem is the factory. So factory usually we call that the Chinese is the 文字馆. Okay, the factory that indicates the cross-section area will change along the flow directions. Okay, and then in other questions, if you mount the delta P, you mount the pressure gauge in here. So you can measure how large the delta P at the different cross-section area. So the cross-section 2 and the cross-section 1. And we actually know there is a different velocity magnitude. Okay? So go back to see the questions. We know that the inside, the material is the water. So the density is the 1,000 kilogram per meter cubic. And we know the area ratios in here. So we have the A2 divided the A1 is equal to 0.5. And since we know that the velocity in the pipe, the V1 is the 10 meter per second. So please find the pressure difference recorded by the pressure gauge. So the question we need to answer is how large delta P we will have, and we observe in the pressure gauge. And again, we assume this is the uniform flow, and the viscosity that are not important. That means the flow is the ideal flow. Okay, so that's the first questions. If we know that the velocity V1 and we know the area ratios, can we predict the V2, how large it is? Yes, we can, because we have the continuity equation and the uniform flow and ideal flow. So we can assume the A1, V1 will equal to the A2 and V2. So we don't know the V2 and we keep on the left-hand side, and this will equal to the A1 and the A2 multiply the V1. And the A2 divided the A1 in here is 0.5. So here the ratio A1, A2 should be equal to the 2 and the 10 meter per second. So we know that the V2 is 20 meter per second. That's we know that the V2 velocity, and the second we should apply the Bernoulli equation, because we wondering to understand how the pressure changes along the cross section 1 to 2. So as you remember the Bernoulli equation, we know that the P1 plus the gamma Z1 plus the 2 over rho over 2 V1 squared and will equal to a P2 and plus the gamma Z2 plus the 2 over rho V2 squared. And you can you know that this is a piezometric pressure at location 1, and this is a piezometric pressure at location 2. So before we calculate, we know which one is large, the piezometric 1 and the piezometric pressure 2. We know that the flow is upgoing, so we actually know there is the high pressure, right? Because the higher pressure will move to the lower pressure regions. Okay, so we know that the piezometric pressure 1 should be minus the piezometric pressure 2. This is equal to the delta P will equal to the 2 over rho and the V2 squared minus the V1 squared. Okay, and we just put all the number inside the equations. So we know that the delta P observed by the pressure gauge will equal to 0.5 and the density is 1,000 kilogram per meter cubic, and the inside is the velocity is the 20 square minus the 10 square, and the unit is a meter square per second square. Okay, so we can use your calculator to compute the final answers. Okay, so as soon as I show the number in here is 150 kilo per. Okay, so this is a very important exercise. Sometimes we should combine the continuity here and the Bernoulli here together to understand what's the problem we meet. Okay, so even though in this chapter we discuss with the continuity equation, but you cannot forget the Bernoulli equations. Sometimes the two equations very important when we looking for our problems and find out the solutions. Okay, so it's very simple, and as we know, I have introduced before for the cavitation problems, and when I discuss the cavitation problem, we will see the plot, the vapor pressure here. So as you can see, we have the vapor pressure on the y-axis, and the x-axis is the temperature. So we have the curvature line. Based on this curvature line, we can identify if the pressure environment is lower this line, and your material phase will change from the liquid to the vapor. Okay, that indicates I can pick out the normal condition maybe here. This is the 15 degree, and then we will have the vapor pressure PV. Okay, so the condition maybe at the room condition, the 14 degree, and maybe the vapor pressure in that conditions will equal to the 1.7 kilopascal. And as you can see, if your environment pressure lower than the PV I showing here, and your liquid will move to the vapor gas. Okay, so how large it is? As you remember, the 1 atm will equal to the 101.3 kilopascal. So you can know that's how much the ATM we have. So the 1.7 divided 101.3, so that will equal to the 0.0167 ATM. And as you remember, the 1 ATM will equal to the 14.7 psi. If you remember what's the psi, the psi is the bond force per inch square. Okay, so you can convert how large psi we will have for the normal conditions. So 0.246 psi. So this is a very important numbers. If your environment pressure lower than the vapor pressure here, and then you will see the liquid will change the phase into the vapor gas. Okay, and what's the problem we will have? When the environment condition is quite lower than the vapor pressure, and then the liquid will to be the gas bubble. The gas bubble. So we have the gas bubble. But the problem is when the gas bubble brokens and will result in the higher pressure. So the problem is when the vapor bubbles brokens, that will induce the higher pressure. And the higher pressure, how high it is, we can have the 800 megapascal. So we can have the 800 megapascal pressures when the bubble broken. So as you remember, 1 atm only equal to the 101.3 kilopascal. So you can figure out how large the 800 megapascal pressure we have. Okay, so the higher pressure will caused by the pressure force, which can destroy the hydraulic infrastructures. As you can see, the fan surface will have some hole. It's caused by sometimes the rotational speed is higher, and then caused by the lower pressure environment conditions, and then the liquid to be the bubbles. When the bubble brokens, will destroy, will induce the higher pressure to destroy the infrastructure service. And then you can see there is a spillway, and the spillway surface there are some broken, also caused by the vapor bubble. Okay, so that's not always the cavitation problem is a killer. Sometimes there are show advantage for the cavitations. Like we can apply the super cavitations torpedoes. Okay, that indicates the cavitation can reducing the contact area, then the torpedoes can speed up, have the higher velocity, because the contact area increase and the drag force will increase also. So if the cavitation can reduce the contact area, and then the drag force can decrease, and then the torpedoes can have the faster speed. And also the cavitation can produce the shock wave, and the shock wave can kill the kidney stone. So it is also some advantage if we can apply the cavitation problem. But the knowledge for the cavitation problem for the engineering is not good. So in practical, we should predict the cavitation where we will have the cavitation problem. So the major idea is if the high velocity will result the low pressure, and when the lower pressure less than the vapor pressure, and you will have some cavitation problem. So how many conditions can result the lower pressure? So the first one, if your elevation increase, so the pressure will decrease. So you may have some lower pressure conditions. And sometimes if your location with the higher speed, so the higher velocity will have a lower pressure, okay, conditions. And also some suctions regions of the bumps. So the suction region have the small cross-section area. Okay, if you remember the region, if the small area, small cross-section area, and then based on the continuity equation, we know that will result the velocity increase. Okay, so some area, if there is a small cross-section area, we will have a higher velocity speed, and the higher velocity speed, and we will result the lower pressure environment. And lower pressure environment, if lower than vapor pressure, you will get the trouble caused by the cavitation. Okay, so this is a cartoon figure show the boundary in here is our vapor pressure. And you actually know the certain cross-section area in here is a small cross-section area. So if you have the too higher speed, and your pressure changes will touch the vapor pressure line, and that indicates at this point will happen the cavitations if the velocity is too high. So you should control the flow velocity to avoid the cavitation problem happen. So for the user, we should decide how the velocity is allowed to avoid the cavitation problem. So we need to identify and predict the cavitation conditions. Okay, so that's the cartoon figure. At this cross-section area, we will generate, if the pressure lower than vapor pressure, so we will generate some bubbles, and when the bubble brokens, and will induce the higher pressure. The higher pressure will broken the infrastructures along the pipe surface. Okay, so we have the one exercise we can try to practice. How can we predict the cavitation problem? So as you see, the problem is we have the ball. So we have the ball, and we put the ball inside the waters, okay, and this is, I can draw the string line. So this is my string line here, and when the string line touch the ball, and will along the ball surface to here. So as you remember, the the point is in here. We call that the stagnation point, right? 停滞点. Okay? And the stagnation point in here, the velocity equals 0. And then, where is the velocity? We have another velocity in here. And sometimes the maximum flow velocity will happen in here. So this is, I can draw this as a U maxima. The maximum velocity is happen on the top of the ball. And there is a string, the free string velocity U0 in here. This is a free string velocity in far away from the ball. We call that the velocity is the free string velocity. So you see what's the problem? We know that the density is a water material, and the density is 62.4. The bond mass divided the Ft cubic. And so please calculate the speed. Please calculate the speed, the U. Okay, calculate the speed, the free string speed, the U0. How large the free string 0? We will observe the cavitation happened at this point. At this point. How fast of the free string velocity, and then we can observe the cavitation problem in here. Okay, and there are some conditions. We know that the maximum velocity is the 1.5 times of the free string. So we know that the relationship is U maxima in here will equal to a 1.5 U0. Okay. The questions tell us the conditions for that. And the condition right now is 10 degrees. And we actually know the vapor pressures. Okay, so at the 10 degree, and the vapor pressure in here is 0.178 psi. A is the absolute pressure. Okay. And we also know that under the free string, the environment, the pressure is the 18. So we know that the pressure P0 here, the P0 is equal to 18 psi absolute. So the first idea, if we know that the blue line is the central line. So the 2 points located at the central line, we can apply the Bernoulli equation. So the first, we have the Bernoulli equations. So we know that the pressure 0 plus the gamma elevation 0 plus the 2 over rho over 2 U0 squared will equal to the pressure at the P maxima. But right now the pressure at this point we replaced by the vapor pressure, because this is the pressure will lower than PV will happen the cavitation problem. So we have a pressure in there, and the gamma D maxima, the elevations at the maxima, and plus the rho over 2 and the U maxima square, right? Okay, and as you remember, in our previous exercise, we usually neglect the elevation difference between the ball. Okay, so we neglect the elevation difference in the center of the ball and the top of the ball, because they cause us only a little bit different changes. Okay, so finally we know that the relationship is so we rewrite the relationship is the P0 minus the PV will equal to the 2 over rho And since we know that the U maxima is equal to the 1.5 times U0, and we can have the square and minus the U0 square. Okay, minus the U0 square. So you can rewrite this as we can have the 2 over rho, and it's 1.5 square, 1.5 square minus the 1. So you have the 1.25 and the U0 square. So our target is the U0, how large it is. Okay, so I first calculate the pressure difference. So the P0 minus the PV, the left hand side, and will equal to the 18 PSI minus the 0.178. Okay, and the unit in here is the PSI. And if you remember, I have said the PSI is 17.822, and the PSI is the bump force per inch square. So we first, as you can see, all the unit is FT. All the unit, they are the FT, and the final answer also the FT. So we should convert the inch square to the FT square. So we have the 17.822, and we know that the 1 inch will equal to 1 inch will equal to the 12. 1 FT will equal to the 12 inch. Okay, so we can multiply. The 12 square, and the unit can change into the FT square. Okay, so you can calculate the answer after we change the unit to the PSF. This is the PSF. Okay, 368, and the bump force divided the FT square. Okay, and then we also know that the 1 bump force will equal to the 32.17 bump mass multiplied the FT and the per seconds. So we calculate the delta P will equal to the 2566.368, and the bump force to change into the bump mass unit. So I multiply the 32.17 to change the bump force into the bump mass, multiply FT divided the second square and divided the FT square. Okay, so this is I change the unit for the bump force to the bump mass. So based on my calculator, it's equal to the A2560 and the 1, and the unit is a bump mass, and the S second square and the FT. Okay, this is our delta P, and then I can put the answer, the delta P inside. Go back to the equations. So the second step, we have the 8256.01 bump mass, and the second square FT will equal to the half the density. Here we have the density. So the 2 over log over 2, the density is 62.4, and the bomb mass and ft qubit, and 1.25 times, and the u0 square. So you can calculate the u0 square will equal to, I check by my calculator. So that will equal to the 2116.9. And the unit right now, you can do the dimensional balance. You actually know it's a ft squared divided the secant square. So you can take a root for this number, and the final is equal to 46.01 ft per second. Okay, so let's if you wondering to avoid the cavitation problem involved in your questions, you cannot have the speed higher than these values. If your velocity flow speed higher than this value, you will observe the cavitation problem. Okay, so that's not related to the continuity equation. It's just some ideas based on the Bernoulli equation. And we know that the higher speed will have the lower pressure. It's just based on the Bernoulli equation idea. Okay, so that's a very good exercise. We can try to practice how can we predict the cavitation phenomena. Okay, so in the next semester we have some Venturi tube experiment. So the idea is you have the tube. So in the you can draw. There is the tube. So this is 文试管 in here, and you can see different along the pipe. You will have a different cross-section area. Okay, you have a different cross-section area along the Venturi tube, and you can see there is a pressure gauge. So you can measure the pressure. You can observe the pressure based on the pressure gauge. Okay, so if you have the continuity equation, so you actually know the A1 V1 will equal to the A2 V2, right? You can just based on this equation, this is our continuity equation, and you can understand the cross-section area changes and how the speed changes. And then you have the Bernoulli equation. So you know always equal to the constant. This is the Bernoulli equation. So you have the Bernoulli equations and you have the continuity equations. You can calculate how difference at the different cross-section area and what the pressure we have and what the velocity we have. And so that's based on the two equations showing here, you will understand the velocity and the pressure relationship. Okay, and then you can compare the result computed from the two equations, and there is true answers. This is a true pressure. You can use the pressure gauge to measure. So it's based on this experiment. Actually, the measurement pressure and the pressure compute based on the continuity equation and the Bernoulli equation are quite different. They are not always the same. That's because in real case, we need to consider the viscosity effect. Sometimes the viscosity effect involved in our problem that indicate the energy will dissipate. So the energy not always conservations. So and the difference between the theoretical pressure and the observed pressure, we call that the loss. the header rules. Okay, so that in next semester you will practice how can we do the experiments based on the idea is two equation, continuity equation and the Bernoulli equation. Okay, and the final topic I wondering to teach is the continuity, but the form is the differential form. And sometimes we call that is the 连续方程的微分形式. Okay, so this is our final topic. And the final topic I wanted to share you the idea. If you remember previous slide, we the chapter we do the cross product with the velocity. The spatial differential operator cross product with the velocity factors if equal 0, and then we will call that the flow is rotational flow, right? But right now, I wondering to, based on the continuity equation, to tell you the one equation's formula very important is the spatial differential operator dot product with the velocity factor can also equal 0. And but what's the physical meanings? So today I wondering to share you the ideas. Can I say some things if the spatial gradient operator dot product with the velocity field is equal 0? What's the physical meanings? Okay, what's the physical meanings? So the first I pick out the one qubit. So this is my fluid particle, but it's a very small qubit. Okay, it's a very small qubit, and I can run in to see how the qubit we have. So as this is the fluid qubit, so I define the dimensional. The right hand side, go to the right is the x, and here is the y, and the top is the z directions. So we know that the velocity in here, we have the u velocity and the v velocity along the y, and here is the w velocity going up. It's the fluid velocity along the z directions. And right now I pick out the one depict the dashed line is right now is my control surface boundary. So this control surface boundary actually is located at the xz plane, right? This is the plane located at the xz plane. And the dashed line is my control surface. So I move to the next, I just project the xz plane. So this is my xz plane, and I guess the control surface the length is delta x. So that means the here is a half delta x, and here is also the half of the delta x. And at the center point, I assume the center point, the velocity multiplied the u is rho u in here. So if the question is we have the two cross-section surface here, control surface here. So there is my inflow, and there is the outflow. Okay, and you can see the area at the boundary is delta x, delta y multiplied delta z. This is the cross-section area, right? It's a delta y multiplied delta z. Okay, because right now we are considered along the x directions. Okay, so the cross-section area for the outflow and the inflow, A is delta y multiplied delta Z. And then here we assume if delta x is small enough, so if we know the low u x function, that indicates we know that the point in here is a low u x function. So how can we predict the low u but the location change x to plus the delta x multiply divided 2? Also, can we predict the low u but the location changes to the minus delta x divided 2? Why I would like to predict the different location velocity? Because I wondering to compute the mass flow rate changes in here and the mass flow rate changes in here. I want to compute the inflow and the outflow mass flow rate. Okay, so based on the tidal expansions idea, we know that if the delta x is small enough, so the low u x but a little bit location difference can be rewritten by the low u x plus the low u dx. We assume the low u changes along the x is linear, and there is a small amount location difference. Okay, and some higher mode items, we have the delta x squared, delta x cubed powers can ignore because the delta x is quite smaller. Okay, this is based on the tidal expansion idea. So the similar idea, how can we predict the low u if the location change to the x minus the delta x half? Again, we have the low u x, but there is the minus and the low u dx and the delta x half. Okay, so that's based on the idea, so we can predict the velocity on the right hand side, outflow cross-section area, and we can predict the velocity on the left hand side is the inflow cross-section area. And so right now we can go back to consider the continuity equations. So we have the inflow and the outflow, so we can compute the delta flow rate changes. Okay, so right now the outflow minus the inflow. If we remember, the outflow is the right hand side, so the velocity is the low u plus the low u dx multiply the delta x divided 2 is the velocity low, and the cross-section area, as I mentioned, is delta y multiply delta z. Okay, so the left-hand side is the velocity, and the right-hand side here is the cross-section area. So the totally there is the mass flow rate, and then we should minus the low u and minus the low u dx and delta x divided 2. And again, the cross-section area is the same, delta y, delta z. So some item you can cancel out is the low u, you can cancel out, and only have the items for the linear gradient. So finally, we only have the low u dx and the dx, dy, and dz. Okay, this is mass flow rate changes along the x directions. So similar, we can write down the different directions. So I change it to the y directions. So the u will change it to the v velocity, and the dy, and again dx, dy, dz. And if along the z directions, we have the low w and dz, and delta x, delta y, delta z. So you can merge the all parameter mass flow rate together. So finally, you can rewrite the equation is the d rho u dx plus the d rho v dy plus the d rho w dz, and multiply the delta x, delta y, delta z. Okay, so right now we just discussed with the continuity equation for the small fluid particle. So that's our target is a final formula will change to the differential form. Okay, so this is only the item for the mass flow rate changes along the x and the y and the z. But if you go back to consider the continuity equations, we still have the items is the mCv dt, right? Previous slide we finished to understand the delta m rate. But right now we change to consider, discuss with the mCv dt. Okay, so the mCv is quite very simple because the delta x, delta y, delta z multiplied together is the cubic volume, right? So you have a fluid density multiply the total volumes will equal to the mCv. Okay, so you can rewrite the equation is dt, but the mCv is rho delta x, delta y, and delta z. And plus the second item is the mass flow rate changes. If you remember, it's the d rho u dx plus the d rho v dy plus the d rho w dz. And the outside is the delta x, delta y, and delta z. And the continuity equation tells us they are equal 0. Okay? And we know that the delta volumes of the qubit cannot be changed with the spatial in the time. So we cancel out. So finally, we can only have the dt is rho plus the d rho u dx and the d rho v dy plus the d rho w dz will equal 0. And you can rewrite the equation for the second items is will equal to the spatial gradient dot product with the rho v factors will equal 0. So finally, this is formula showing here is our continuity equation, but the differential form. OK。这就是最后的连续方程的微分形式。Okay, so maybe we have a 10 minutes break and we go back to see what happens for the continuity equation of the differential form. Okay, 那我们休息一下。